Okay. Sorry about that. So today we're going to discuss, as I said, we're going to discuss about three things. One is name-based classifier, and number two would be about homework 3, and number 3 we're going to discuss about one very interesting problem. Like to give you an example of how difficult or how easy the midterm exams are going to be. So these are the three things that we'll be discussing. Before moving forward, any questions from previous discussions or anything?
I have a bit question.
Mm-hmm.
The home for the midterm, it will be the web scan, and also only allow the one sheet that you will provide to us about the formula, right?
Yes, we will give you a cheat sheet which you can utilize it during the midterm. Apart from that, you're not allowed to use any other sources.
Okay. And also, is the calculator allowed?
Is what?
Calculator.
Calculator is allowed, yeah.
Okay, thank you.
Yeah. Any other questions? Okay, if there are no questions, let's quickly jump into name-based classifier. So let me just share my screen. Okay. This Zoom has too many. Okay. Okay. So what we'll do is we'll use the same. Yeah. For today's tutorial, also we'll use the same data set that we've used before for logistic regression. We'll be using the Titanic data set. So as always, let me first unshare the screen and try to explain on board what's the problem that we're trying to solve. And from there, we'll build how it is different from logistic regression and other things. And from there, we'll actually see how this works. This should be a relatively easy tutorial to do because we're not going to concentrate very much on the math part of it. We're just trying to concentrate more on the implementation part of it. So is the board I'm trying to yeah is my board visible to everyone clearly? Yes, awesome. So if you guys remember previously for the problem that we defined, what we're trying to do is we're trying to predict based upon different biological or different other features. We're trying to predict whether a person in a Titanic will be survived, what are his chances of survival or not. So that is the classification problem that we're trying to solve. So if we forget about all other features and if we just concentrate on one feature, let's say that feature is age. And let's say there is another feature now let's say this is the y variable for you, which is nothing but whether a person is survived or not. It will take, let's say, two values, 1 or 0. Right? So there can be different. So if I plot some data points on these axes, let's say from age, let's say 0 to 15, majority of them are survived. So and from age 15 to 25, not survived, and from age let's say 45, from 45 and above, they survived. So let's say the distribution of the data is something like this, right? So what we have done in the previous classes or in the previous discussions is we try to fit a line which determines which creates a class boundary between these variables. Like something like what we try to do is we try to fit a line which will give me some kind of a boundary between what is a positive label and what is a negative label. So essentially, if I write it in terms of probability, what we're trying to do is we're trying to figure out given features X, like given age, we're trying to predict what is the probability of what is the probability that a person is survived or not survived, right? So that is what we are trying to do in our previous discussions, right? So whenever you're doing something like this, there is a general class of these kind of algorithms. They are called discriminative models. So what you are essentially trying to do is you're trying to fit given the feature vector, you're trying to predict y. So that is what's happening. But from now on, from here, what you will do is we are going to enter into a different type of different set of algorithms called generative algorithms. So what are generative algorithms? So here, given X, we're trying to predict Y. Like given age, we are trying to predict Y. But in generative algorithms, what will happen is we'll try to figure out given Y, we'll try to figure out what are the features that will fit Y. What does it mean? Given that a person has survived, what can be his attributes? So we're just trying to invert this, and this is called a generative modeling approach for machine learning algorithms. So think of it like this. Let's say there are positive labels, and let's say these are all positive labels and these are all negative labels. Previously, what's happening is we are trying to find a decision boundary like this, and we're trying to say, everything above this line is positive and everything below this line is negative, something like that. So, but if at all we are using this generative approach, what we'll be doing is we'll try to figure out a decision boundary, or we'll try to find a distribution that fits all these values, and based on that distribution, we'll try to predict whether given a new feature vector, whether something is right or not. So that's essentially what's going to happen. So there is one very beautiful algorithm that is given. So like if you remember your Bayes theorem, P of A given B is equals to P of A intersection B by P of B, right? So this is your Bayes theorem, and so this is how it works. Now, what else is there to discuss? Okay.
How what works again?
Yeah, any question?
No, I mean, like, this is how what works again, like this whole thing.
Yeah. So what will convert this P of X given Y into this? I'll show you the formulas in exact manner how they'll be derived. But so what will happen is we'll figure out P of X given Y. If I write it in this form, we'll try to figure out P of X given Y, like saying, so if I write this, X is actually a feature vector, right? It's not a single valued variable. It's like multivariate. Like X is a vector X1, x2, x3 like that. So when you're trying to predict, like given y, we are trying to predict what is the value of x. So it can be written as p of y given x p of y given x equals to p of x given y into p of y. Yeah. So this is essentially what we'll try to formulate. So here, since x is a feature vector, we'll take a naive assumption that x values are independent to one another. So this will kind of p of y is like a prior probability. It's kind of like a constant. So it will basically turn into something like this: p of x1 given y and p of x2 given y. So something like it will turn like, instead of it being parameterized by all the values of x1, it will just be, since we are assuming that x1, x2, and x3 are independent, it will just be a single distribution like that, right? So let's actually go through some examples. Then I think it will be much more clear. Yeah. Okay. Yeah. So in here, I told you, right, like we are trying to, if at all we are going to predict like p of y given x, it can be written as using base rule p of x given y into p of y by p of x. Did I forget to write p of x? Yeah. So when p of y is like the probability of observing class y, and p of y is basically prior probability, it means like let's say in this Titanic data set, if at all, let's say there are 100 positive labels and 200 negative labels, the probability of y equals to 1. Like probability of y being a positive label should be 100 by 300. So yeah, that is like a prior probability. And p of y given x is when we observe an instance x, what the probability that it belongs to class y. So given x, like what is the probability that what is the probability of occurring y. So this is what so in our data set, if at all p of y given x1, x2, x3, and so on, we are trying to figure out, then it is something like this. So what is the naive assumption that we are assuming is so p of x1, x2, x3, all of these are independent random variables. So then you can deconstruct into a product using like the product rule. You can just say p of let's say there are a total of m feature. Let's say there are m features. Then it will become j equals to 1 to m p of xi given y into p of y. So essentially from now on, it's basically the same step. So what we will do is we'll again apply the same maximum likelihood estimation and try to figure out what is the weight function. So that's how naive Bayes also works. Now, as I said, there are different distributions. Like here, I just said the probability of xi given y, right? So the thing is, the probability distributions can be different types of probability distributions. It can be Gaussian distribution that we can assume, like a bell curve normal distribution we can assume, or it can be a multinomial, or it can be Bernoulli. So there can be different types of distributions that we can assume for the data. So what I mean is, like, for predicting this positive labels, I can just say it is following a certain distribution called normal. Since we are kind of assuming that it follows a certain distribution, your computation will kind of will be lesser, and in general these models are a little bit faster than the logistic regression things. But since you are assuming, that means you're also inducting some bias into the system, which is why they might not be the best case in all kind of model that you use. So so let's just go to the implementation once. Okay, so the first few steps are basically some they're just basically the data pre-processing steps. I think we have already seen this step, so I'll just quickly skim through all these details. We are just importing pandas data, and we are just dropping all the things that we don't want, and we're just using these three labels, or these three features, for our classification purpose. So our target variable is essentially whether a person is survived or not. Now here we have two types of variables. One is categorical and one is numerical, right? So here age, fair, and P class. So here another thing we need to keep in mind is here P class is a categorical variable. It's not a numerical variable, because classes can be like 1, 2, let's say 4. So it's already written like 1, 3. So it is a categorical variable, not a numerical variable, but age and fair are numerical variables. So again, we'll do pd.getDummies, and we are using just one feature vector to represent whether it is a male or female, because it essentially means, if at all it is 0, then it is if at all it is 0, then it is male. If at all it is 1, then it is female. So you don't need dummy variables to represent. So you just need binary, because this is like a binary classification problem. You don't need more than 2 values to represent your prediction category, right? So what else is there? Okay. So here we are just inputting the age, if at all there is any age which is missing. I think we have already done this before. We're just trying to fill it with the mean age value. So here we are using scikit-learn train test split to first split the data into training data and testing data. And I said there are multiple different naive-based classifier. If you go to scikit-learn official website, there are various implementations of naive-based. It can be naive-based, it can be Gaussian NB, it can be multinomial NB, it can be something else. So you can visit the scikit-learn documentation to see what are all the things that are there. We're defining that model, and here I haven't scaled the data, but in your implementation and homework, you guys should scale the data. So once we fit the data, we're trying to get the accuracy score for our prediction. So we got somewhere around 78%. So I think you can so again, then we did just a simple cross validation, and we printed the cross val score. I've already explained in the previous discussion what cross validation is. So if at all we put like cross validation, n-fold cross validation equals to 5, we get like 5 accuracies. And if at all I wanted to take the best out of all this, so on an average, the accuracy is about 80% classification accuracy. So that is kind of okay for what we are trying to do. Any questions so far? Or is it?
Wait, can I look through the lines of code again for a bit, or some of them? Also, when are these files being uploaded onto the Canvas page?
Yeah, they'll be uploaded immediately after the discussion. What do you have any specific doubt, or is it just like, should I skim through from naive Bayes?
So like the new stuff is like the Gaussian NB function, yes. And then like fitting, scoring, and
it's the restore is actually kind of the same thing. So the good thing about scikit-learn, using scikit-learn for naive Bayes, support vector machines, and all this is it abstracts a lot of internal stuff for you, because we're concentrating mostly on the implementation part for discussions or for your homework. So we're not building this from scratch. And we also don't have that much time to build it from scratch. Had it been like we had some previously, we used to have 1.5 hours of time to teach this building. So where we used to build everything from scratch. So that's where, if you see the previous discussion materials, we have actually created everything from scratch. We have defined each Gaussian classification, how to compute Gaussian, how to predict the probability. So all these things are already there. We have uploaded this thing as a supplemental notebook, but for this class, as of now, we are primarily concentrating on implementation mostly. Yeah. But this material is also available for you on Canvas as of now. Any other questions? Did I answer your question, or is it overboard?
I mean, like, I guess I'll just like, I'll also try looking up some of the way, how to use some of these like on Google.
Yeah, sure. That would be a good practice too. If you guys have any specific doubts of internals, how anything is working internally, feel free to come to my office hours. I'll explain them in detail with mathematical equations if possible. So yeah, now let's quickly go through homework 3, because we have 2 more sections that we need to cover. Now in homework 3, it's kind of similar. It follows a similar pattern as homework 1 and homework 2. So we're essentially giving you a data set, and we will ask you to do some pre-processing. Then we're asking you to fit a naive Bayes or different classifiers. I think in homework 3, we have 2 things that you need to apply. One is naive Bayes classifier, and the second one is support vector machines. I think I'll not talk about support vector machines as of now. My other TA, Dishan, will talk about support vector machines. So 1 second, let me. So this in this homework, we have a government industry data set. Essentially, what we are trying to classify is based upon the productivity. We're trying to say whether a particular person or particular department is productive or not. So that's essentially what we are trying to do. So these are all the features that we have in this, and we've so first of all, what we need to do is we need to do some pre-processing. So there are certain pre-processing steps involved in this. Like first one is like dropping the data, printing out all categorical variables. And here we have to create another column called satisfied based upon actual productivity, because actual productivity is kind of a continuous variable. We are kind of discretize it based upon a set threshold. So we've already given you how to create that function, and you have to create the satisfied column. And then you have to print out if there are any columns which have null values. So this is a general pre-processing, general data pre-processing steps that are that you should do. And coming to the next part, after data processing is complete, here many people usually what mistake they do is we clearly ask them to encode only the categorical variables and do the training. But usually what happens is they use all the variables. So you have to use only the categorical attributes for 2.1, and I think so sorry, for 2.2. So 2.1 is kind of additional data processing for categorical variables, because you have to do for categorical variables, I think you have to do one hot encoding. Yeah. Okay. I think here we are asking you to, you can just use ordinal encoding, not even one hot encoding. So you can, this is like label encoding you can use. Meaning, for example, let's say there are these three classes: Paris, Tokyo, and Amsterdam. You can attribute Paris to 1 and Amsterdam to 0 and Tokyo to 2. And you can just use these as the labels for your for that particular attribute column. So it's just label encoding that you're doing here. Now, 2.2 is again naive-Bayes classifier for categorical attributes. Yeah, like you have to take only the categorical attributes. You have to filter out both categorical and numerical into two separate things, and you have to train the first classifier in categorical itself, and then you have to do separately for naive-Bayes for numerical attributes. Oh, 1 second, just. I think next week we'll discuss about the second part of homework 3, support vector machines. So that's it regarding the homework 3. Any homework 3, first part of homework 3. Any questions here? Okay.
Well, I just get asked. So this time we're not just running as such a long time as the last homework, right? Or
I didn't get your question. Can you repeat?
yeah, for the in the past homework duties this week, it just cost a very long time to run because we trained the machine. But for this time, I think it will be not just cost such a long time, right?
Yeah, I don't think it will take that much of a time, but it depends upon how you process your data.
Okay, thank you.
Yeah. Any other questions? Okay. If there are no questions, let's see one question that's like very interesting and which might be useful for your preparation for midterm.
I have one question for the midterm.
Yeah.
What material we will cover in the midterm? So just from the first class until now?
Yeah, not until now.
I mean, I mean that's from the from the lecture, like the first lecture until today's lecture. Is all we cover? Oh yeah, I went to that. I said it. Yeah, thank you.
Yeah, I think the professor did mention in the class. I think it should not I think till neural networks, I'm not sure. I think you can ask professor regarding that. So it's logistic regression, normal linear regression, and perceptron model and multi-layer perceptron. I think these are the four major topics that are covered for the midterm. I think that's what professor might have in mind, but you should clarify it with her once again. Okay. And any other questions? Okay. If not, let's solve this this problem. Okay. So so this question is about regularization. So let me just read through the question, and we'll use the board later on to solve this question. It kind of looks very easy question, but it becomes kind of tricky when you actually try to solve this. So this is called Tikhonov regularization. Essentially, it's a different implementation of what lasso and ridge regression that you do. So given so they use a similar regularization parameter lambda, but instead of scalar, they use a real square matrix called tau. So this is called the Tikhonov matrix. Given a design matrix like this and a vector labels y, a regression algorithm finds the weight vector W star that minimizes the cost function. So the cost function is already given to you. J of W equals to XW minus Y whole square plus tau W whole square. Let's say that. Now, these are matrices, remember? So these are not direct X and Y values. So these are actually matrices that they are there. Now, they're asking you to derive a normal equation for this minimization problem. That is, in the linear system of equations, find the optimal weight vector. So essentially, what we are trying to do is we are taking this function g of w, and we are trying to figure out what are the optimal values of w. What is the optimal values of weight? Let's use the board and try and solve this problem. Let me start sharing one side of the equation on the board. So fine. So G of W equals to XW minus 1 whole square plus is the board visible? Okay. Wasn't Prof supposed to add a new midterm study, right? Since we have last year's. Yeah, I think most of the concepts are similar. I think that's why the Prof might have added the same thing. But yeah, you should again mail the professor if you feel something is not being covered. Okay, so if at all this is the weight function, essentially what we need to do for finding the optimal W, let's say that's W star. We're trying to figure out what's optimal W. For figuring out optimal W, what we need to do is we need to do j dash of w, and we should be equating it to 0, right? So that's what should happen. But as I said, so these are not direct scalar values. These are vector representation of scalar values. So so how do you differentiate this equation? If I ask even like a question like, if you remember in normal way, if we represent y equals to j, if at all, let's say there is a function j equals to x square. This is the function. Let's say this is j of x, and if at all j dash of x, x square minus 4x. Let's say this is a function. If at all we are trying to find the minima or maxima for this function, we'll try to derive it. That will become 2x minus 4, and if we equate it to 0, that will become 2x minus 4 equals to 0. That means x equals to 2. So this is how you do it for a single variable univariate optimization problem for a given function g of x. But in this scenario, when you are computing it with g of w, your j dash of w will become something like this. It will become 2 here. J dash of w means you are differentiating with respect to w, and w is a parameter. W is a vector of weights, something like w1, w2, w3, like that. So it's a vector. It's not a scale. So so here x will be a coefficient. So if you assume this whole thing as a value or something like u, so it will become what? If I assume this whole value as u, let's instead of trying to figure out everything at once, let's first compute the derivative of this, and then let's compute the derivative of this. Let's say we are computing the derivative of this. That is nothing but derivative of dou by dou w of xw minus y whole square, right? Now, instead of computing the derivative of this directly, we can use chain rule. And let's say I'm assuming that xw minus y is equals to u. Okay. Now we know that dou f by dou w can be written as dou f by dou u into dou u by dou w, right? So if I say u equals to this thing, what will your dou u become? It will become x transpose, because when you derivate this function, the coefficient of w is x, but since it's in vector form, and if you do a calculation, it will come in a diagonal form, and if at all you do dou u by dou w, it will essentially be x transpose. So this whole value dou u by dou w will become x transpose, right? And if at all I do dou f by dou u first, what will this become? This will become 2 into x transpose into xw minus y. This is the first value. Now, what is the second value? 2 into, similarly, if at all I use the same strategy what I've used here, this will become 2 into tau transpose into tau into w, right? Any questions? So now we said j dash of w should be equals to 0, right? If I equate this whole thing to 0, essentially the w that we'll get here should be the w star that we're looking for. Right? So if I equate this whole thing to 0, then it's essentially x transpose x into w minus y into x transpose plus tau transpose tau into w equals to 0. Right? So that means tau transpose tau plus x transpose x into w equals to y into x transpose. So that will essentially give me w equals to tau transpose tau plus x transpose x whole inverse into x transpose y. So this is the weight vector, which is the optimal weight. So that's essentially what the question has asked. So it's basically a very similar concept of what you have learned, a similar optimization problem, like where you have a function of theta, g of theta, and you compute j dash of theta, and you equate it to 0. The only complexity that you see here is because these are matrices, you should know that dou w dot product of x into dou w is something like x transpose. So I think this kind of chain rule implementation is something that is very different. That's why this question can be classified as a little hard. So yeah, any questions?
This kind of stuff going to be on the midterm?
I think 1 or 2 questions, not many, but
can I take a screenshot of the whiteboard for a moment?
Yeah, I think the video will be anyway uploaded, so you guys can do it from that. Or yeah, you can do it. Yeah. So.
Thank you.
Any other questions? Okay, I think if not, we've completed it a little early for the first time, I guess. So if you guys have any other questions related to midterm or something, I think I can